approaching this problem using VT graphs, we are going to be looking at three different types of graph, although it will be the VT that we'll use. So we've got displacement, and we've got velocity, and we've got acceleration. And it doesn't matter what order you draw these in. The thing that I would notice first is that we have constant acceleration, 6 meters per second. So that's always 6. That's very easy to draw on. That means that because we've got constant acceleration, we've got a straight line graph or a VT graph. So we're starting at 2 meters per second and going up to 5 meters per second. So the gradient of this line is going to be 6 across 1 up 6, because this the gradient of the VT graph at any point is the value of the AT graph at that point. So what about our displacement time graph? Well, you should know by now that this looks like, well, it is a quadratic. S equals ut plus a half at squared, or S equals vt minus a half at squared, both quadratics in t. And the gradient of the st graph at any point is the value of the VT graph at that point. Notice that whereas the gradient of the VT graph is always 6 across 1 up 6 across 1 up 6, the value of the gradient, the steepness of the curve for the ST graph keeps changing, and that's why the value of the VT graph keeps going up. So we're actually looking at the gradient of the tangent line, which gets steeper and steeper, and we'll be using that later when we've done some calculus. Anyway, looking at this question, the fact that we're going to use first of all is that the gradient, there's only two facts, so we're going to use the first one first, that the gradient of the VT graph is equal to the acceleration. And so I can say, well, my final velocity there was 5, my initial velocity there was 2. So the change in the velocity here is 3. 5 minus 2 is 3, divided by the time here, which I don't actually know, but I do know that this is 6. So that gives me 3 over t is 6, so t is a half. So it's only half a second long, this particular thing. Okay, next fact I'm going to use is that the area under the VT graph is equal to the displacement. And I know the formula for the area of a trapezium. It is these two parallel bits added up. So that's going to be 5 add 2. And then multiplied by half the distance between them. And the distance between them in this case is t. And t is a half. So I'm multiplying them by half the distance between them. And that is going to give me 5 add 2 is 7. 7 divided by 7 times 1 is 7. 2 times 2 is 4. So the displacement is 7 over 4 meters, and the time taken, not that we needed that, but is half a second. Now let's try the same thing using SUVAT. So let's see which one we prefer. I'm going to assume that my particle is going to the right, and I'm going to take that to be positive, which means that what I'm looking for is S, which is going to be positive. It starts with a velocity of 2 in that direction, the positive direction, and ends with a velocity of 5 meters per second in the same direction. It hasn't reversed, and it's getting faster in that direction, which means it's accelerating, and it's accelerating with 6 meters per second. I'm going to use the formula without t, which is v squared equals ux squared plus 2as, and I'm going to stick everything in. So I get 5 squared equals 2 squared plus 2 times 6 times the displacement. So 25 equals 4 plus 12s. So s equals 21 over 12, which can be simplified by dividing by 3 to 7 over 4 meters. Now in this case, I have to say I prefer the SUVAT method, but really, really simple, really clean. But I also think that a lot of times the VT graph approach is actually better and simpler than the SUVAT approach. So always have both in your mind as being good, not one better than the other. And this is for periods of constant acceleration, don't forget.